There are three basic types we discuss in our classes. That is, first one is reflexive relation. We can take some real life examples to understand these types. Okay, reflexive. Then we have symmetric. Okay, then we have transitive. And what are these? We'll understand one by one. So let's start with the reflexive. Shall we? What is a reflexive relation? First, let us understand the mathematical definition of a reflexive relation, and then we'll apply it to the real life example. Read this. See, here there is a set A and there's a set B. Set A has same element as set B. This is not a condition, but here what are the relations? A is related to itself, B is related to B itself, C is related to C itself. Such a relation is reflexive relation. See this? Set of all ordered pairs in such a way that an element is related to itself, that becomes a reflexive relation. If x comma x belongs to R for every x, that's very important. It's not for only one element. For every element in this A set, it has to be related with the same element in another set. Such a relation is called a reflexive relation. And you can remember this with the word reflexive itself. Say it is coming from, it's just a keyword from the word reflection. When you see a mirror or a water, you see your own reflection, right? That means in the reflection, what you see is yourself. That means you are being related to yourself in the image. Same thing here. Letter A is related to itself, B is related to itself, and C is related to itself. Right? Is that clear? Let me give a simple example in the mathematics itself. Equal to, it can be a relation which can be a reflexive relation. Every number is equal to itself. Yes or no? Do we have any doubt in that? This is one example. Can you come with some more example like this in the mathematics? Let's not get into outside mathematics. In the mathematics, every number is equal to itself, right? So it's a reflexive. This relation is a reflexive relation. Okay. Then I can write like this: set of all A comma B such that A is equal to B. This is a relation which is a reflexive relation. Right? Any example? Any more example? Yes. Parallel to. Set of all lines L1 comma L2 such that L1 is parallel to L2. That's a reflexive relation because we know every element, every line is parallel to itself. That's a reflexive relation. Okay. So there are some more example here. A relation of parallelism of lines on a set of all the straight lines in a two-dimensional plane. Yes, that's what I was discussing here, right? And next, what we have: triangles relationship to one another and to set of triangles. So, for example, triangles relationship, maybe I can say similarity. I can use this relation, similarity. You know what is similarity of a triangle, right? Every triangle is similar to itself or not? Yes. And I can also say congruency. Every triangle is congruent to itself. So this relationship in triangle can also be reflexive relations. Okay. Apart from equal to, there is another thing: greater than or equal to. Relation of greater than or equal to two set of natural numbers. Instead of equal to, I can say greater than or equal to. Right? Every element is either greater than itself or equal to itself. So we can use greater than, we can remove it because we also have an option to say equal to, right? Similarly, because equal to is involved here, I can say every element is less than or equal to itself in a natural number specifically. Okay. Hope this is clear with the reflection. Just remember the word reflection. So it's a key word to remember. What is reflexive relation? In both the places in the ordered pair, we need to see the same element, reflection of this. So that is reflexive relation. Okay. Hope that is enough to understand what is reflexive relation. Let's go for the next part, which is which is the next type of relation, which is symmetric relation. What is symmetric relation? So you can remember with this word, say we call it as axis of symmetry. In case of coordinate geometry or parabola, we use this word axis of symmetry. What is axis of symmetry? If there is an image here and I want it, what is the axis? If there is a same reflection of that on the other side, or maybe if there is an image, a parabola, a symmetric parabola, I can see exact symmetric nature of this curve on the other side. So this axis become axis of symmetry. So if you see a particular image from the reverse direction, it should just look like the same but in the reverse direction. That is what symmetry is all about. So to keep it very simple, let me read this. If x1 comma x2 belongs to the relation, which must imply x2 and x1 must also be in the relation for every x1 as well as x2. Maybe I'll give an example. See here, if a set has some elements 1, 2, 3. Okay. Now if the relation has 1, 2, then it must have 2, 1 also. If the relation has 1, 3, then it must have 3, 1 also. For every element, that means what? Even if I have 1, 2, 3, then I must have 3, 2. Suppose if I have only 2, 3 and I don't have 3, 2, it will not become symmetric. Okay, symmetric relation. This is an example. Okay, see here. One example in the mathematics from the geometry, just like I discussed parallel, I said perpendicular. So there is a line here. Say, let it be line 1, let it be line 2. Is line 1, assuming it's a 90-degree here, line 1 is perpendicular to line 2. It's a relation. Can I say line 2 is also perpendicular to line 1? Yes, that is the relation. Okay, so if L1 is perpendicular to L2, definitely L2 is also perpendicular to L1. So it is what? This is symmetric in nature. Can I also say parallel to a line L1 is parallel to L2? That also indicates L2 is parallel to L1. Remember, parallel to condition is also reflexive. Parallel to is also, this relation is also symmetric in nature. Okay, a triangle's congruency with respect to set of triangles. Yes, if a triangle T1 is congruent to triangle T2, I can say triangle T2 is also congruent to triangle T1. So if you have, in case of reflexive relation, we were using only one element. Here we are bringing two elements and we change the order. The relationship still remains the same. Such a relationship is called symmetric relationship, right? Yes. So figure 1 is symmetric but not reflexive. Can you see? This is symmetric but not reflexive. So what are the ordered pairs we have? A comma A. So I can rearrange them. It means the same thing. And I see A comma C. Also I have C comma A. I also have B comma B. So it is, they are telling it is symmetric but not reflexive. Tell me why it is not reflexive. What are the elements we have? A, B and C. Right? So A comma A exists. So reverse also exists here only. So it is symmetric for A. A comma C exists. C comma A exists. So symmetric in that pair also. Right? Yes or no? But it is not reflexive. Why it is not reflexive? I'll tell you why it is not reflexive. Is because we don't have C comma C. As it is missing, it is not reflexive. Reflexive is possible only if every element is being repeated. Right? Now the next one is figure 2 is symmetric, not symmetric, but reflexive. So because A comma A exists, B comma B exists, C comma C exists, but we don't have, we have A comma B also, whereas we don't have B comma A. As it is not there, it is not symmetric. So these two examples are very easy to understand the difference between reflexive as well as symmetric relationship, as well as the common thing between these two relations. I hope this is clear. Let's quickly go to the next part. I think I have some questions here to discuss. In the next section, we have question. Okay, coming to, yeah, we can discuss one important question here, which is very important in terms of the formula we are using here. Just remember this part. If a set A has n elements, remember number of reflexive relations on A is given by 2 power n into n minus 1. How, why, we don't have time for that, and you don't have to. If you are curious enough, you can check why this formula came. But remember this formula, the number of reflexive relations on A, which has n element, is given by 2 power n into n minus 1. Similarly, the next part is, which is very important for this question, number of symmetric relations on A is given by 2 power n into n plus 1 divided by 2. Okay, so this is what is needed for me now. See the question. The number of symmetric relations on set A, which has how many elements? Set A has these elements, so 1, 2, 3, and 4. So how many elements are there? N of A is how much? 4. So according to the formula, we have 2 power 4 into 4 plus 1 divided by 2 in the power itself. So what we get is 2 power 2 into, what do we get here? 5. So what is your answer? 2 power 10. Which option? The option is A itself. Right? So please make a note of this. If you don't remember, make a note of this. Very important formula, which might save you easily by getting 1 mark with no effort if you know the formula. Okay, how and why? You can do a research if you're really curious about it. It's very interesting to know it. But from the exam point of view, we can just stop it here by remembering the formula. Fine. Let's go to the next section. We discuss symmetric. We discuss now reflexive. And coming to the third type, which is more interesting, that is transitive relation. What is transitive relation? If an ordered pair x1 and x2 belongs to the relation, for reflexive we had only one element to show, for symmetric we had 2 elements to show, here transitive we need minimum 3 elements to show. See here, if x1 and x2 is in a relation, they are related, and x2 and x3 are also related, then definitely x1 and x3 must be related to make it transitive. For example, say 5 is greater than 3, right? And 3 is greater than 1. So I can say generally, if A is greater than B and B is greater than C, does it imply A is also greater than C? Yes. So this is a relation which is transitive in nature. Okay. Similarly, I can say less than. Okay. I can also use greater than or equal to, less than or equal to, and divisibility. For example, to a set of natural. For example, say 10 is divisible by, let me take a number. 10 is divisible by, let me take a different example. Wait. For divisibility. So let's not take a number. Let's take an example. If x is divisible by y and y is divisible by z, does it imply x is also divisible by z? Yes. So it is a transitive relation. Okay. So That is enough for us right now. And what is anti-transitive? There is a small term we need to know, which is anti-transitive. So one that possesses the polar opposite of transitive property. What is the polar opposite? That is, if exactly opposite of transitive. If x is related to y and y is related to z, that implies x is not related to z. That is the opposite of transitive function. X is not related to z. Such a relation is called anti-transitive. This is of less significance for us, but just remember what is anti-transitive. It is exact opposite of transitive relation. Okay. Hopefully this is clear. And remember, if a function is reflexive, sorry, if a relation is reflexive, sorry for that, and if a function is symmetric, sorry, again, my bad. So a relation, specifically I'm writing, a relation is reflexive, symmetric, as well as transitive. If all the three are applied, such a relation, we have a very interesting word, equivalence relation. Equivalence relation. Okay, can you give any example which is equivalence? Yes, equal to. A number is equal to itself, right? If A is equal to B, it also implies B is equal to A. So A is equal to A itself. So reflexive. A is equal to B implies B is equal to A. Symmetric. If A is equal to B and B is equal to C, which implies A is equal to C. Transitive? Yes. So this equal to relation is also what now? Equivalence relation. Right? Any other example we have come across which can be reflexive, symmetric, as well as transitive? Yes, that is parallel to. In geometry, if a line is parallel to itself, yes. If a line L1 is parallel to L2, and then L2 is parallel to L1, so symmetric. If L1 is parallel to L2, L2 is parallel to L3, L1 is also parallel to L3, so it is transitive as well. So it is also an example for equivalent relation. What else? Congruency is a relation which can be equivalent. A triangle T1 is congruent to T2. A triangle is congruent to itself, first thing. So if a triangle is congruent in one direction, it is also reverse direction also it is same. So it is symmetric. Also, if three triangles are taken, T1 is congruent to T2 and T2 is congruent to T3, then obviously T1 is congruent to T3, right? So we can keep on giving examples. So it is better you check more examples, right? So let's go to the next part. So we will see some questions on this quickly. Okay. So consider a non-empty set. If the question is visible to you, please read this clearly or let me read for you. Consider the non-empty set consisting of children in the family and the relation R is defined as A is the very interesting example. Let's see if we can answer this. A is the brother of B. Look at the options. They're saying A is symmetric but not transitive. It's a very tricky question. Before answering, please think and answer. I will give you 10 seconds. What is the trap here? Please try to understand. Not just understanding mathematics, a little bit of a very simple common sense will help us to not to make a mistake here. So A is a brother of B. If A is a brother of B, firstly, can anybody be brother of themselves? Can A be brother of himself? If A is male, can A be brother of himself? No, right? A cannot be brother of himself, so it is not reflexive at all. Forget the option. Without option, I'm talking about can it be reflexive? It cannot be reflexive. Okay. Suppose if A is the brother of B, does it mean that B has to be brother of A? Think. If A is a brother of B, does it mean that B has to be brother of A? Must be? Yes. Cannot be sister? Possible, right? Yes, that's what I'm saying. A simple common sense. If A is a brother of B, doesn't mean that B has to be brother of A. B can be sister. So it is not symmetric. So definitely not symmetric. Option A is ruled out. Okay. Now A is a brother of B. Okay. Now B is the brother of C. Can I say A is the brother of C? Definitely, yes. So because A is already male, A cannot be sister now. If A is the brother of B, and now B is also brother of C, definitely A is the brother of C. So it is definitely, what is it? Transitive. So definitely transitive, but not symmetric, but not reflexive. So which option? Which option? Option B. Let's look at the other option. Option A is anywhere wrong. What about option C? It is saying no, neither transitive nor symmetric, which is wrong. And both symmetric, transitive, that is also wrong. The only option that's correct answer is option B, which is transitive but not symmetric. Is that clear? I hope everything is going well. Let's quickly go to the next part of this class, which is very important. That is types of functions. I hope the relation part is clear for you. And this basic understanding of relation is very, very important.